you can underflow, right? These are small numbers that get multiplied together, right? Which means as you go further down in the sequence, the numbers get geometrically or exponentially smaller, right? Which means you might underflow very, very quickly. So what people actually do when they run the Viterbi algorithm is they use log probabilities, not probabilities. Since everything is conditionally independent, everything's just multiplied together, you just take the log of everything and just sum them up instead of multiplying them together. You can get the same answer. With logs, this accumulates additively, not multiplicatively, and you do not underflow. Some people take a negative log and turn this into odd min, but it doesn't really matter. It's all mathematically equivalent. Okay, so just to recap, right? We have independent classification that predicts every token, part speech act token completely independent of the other predictions. You run into this type of error because it doesn't model dependencies between predictions. Right? Mistakes due to not modeling multiple words. Right? What Viterbi gives you is the ability to, for hidden Markov models, the ability to model pairwise transitions. So you can model this guy directly consider adjacent words, right? And Viterbi gives you the ability to, if you can model adjacent words well, you can make a good prediction, assuming that you can, assuming that this model is a good model, and you can do it efficiently. Right. Any questions? Can anyone tell me the running time of Viterbi? Yeah.
Is this something like O of length times part of speech squared?
Yep. It's the running time is the length of the sentence times the number of part of speech tags squared, which is not exponential. Okay, so I'm going to talk a little bit about training HMMs. Imagine a supervised case where we're given all the Y's, right? For every sentence, someone gave us the part of speech tags, right? The goal is to train the parameters of our model using S, right? We want to train using maximum likelihood. Just an aside, it's often useful to, and this is also the case in the naive Bayes lecture, it's often useful to sort of write out these probabilities in terms of, in a matrix form, so you don't have to do a bunch of for loops, which makes everything super slow, because matrix multiplies it much faster. So A sub AB, you can think of it as the probability, or sometimes depending on what you're doing, it could be the log of the probabilities. And this is the transition matrix, this is the observation matrix. And so we could write this guy as something that looks like this. We have matrix, it's in matrix form. Or the log probability version. Nothing special is going on right here. Okay, so it turns out that if you, and I won't make you go through the math, if you wanted to solve the parameters of the hidden Markov model to maximize the likelihood on the data, which is this guy, it turns out that you just need to estimate you can just estimate each component independently, right? And you can derive this by minimizing negative likelihood. You don't need to worry too much about that. But if you're interested, I'll put some resources on the web for that. What does it say? It says I'm going to go through every example, every sentence in my training set, and I'm going to look at every token in that sentence. And this is going to be a 1 if I observe a transition from part of speech tag B to part of speech tag A. Right? And I'm going to divide by the number of times I observe part of speech tag B. This is literally the fraction of times I observe part of speech tag B and I go to part of speech tag A. Right? The maximum likelihood formula has a closed form solution where you just take a count. Just like in naive Bayes. For the observation matrix, it's very simple. It's simply the fraction of times I am in part of speech tag Z and I observe word W. That's it. Super easy, just counting statistics. I will briefly, okay, I lied. I will briefly go over why, although I'm running a little bit short on time, so I'm going to skip it. I will skip that in the interest of time. Okay, so now unsupervised training. Suppose now this is all we observe, right? Just a bunch of X's, no part of speech tags. We still want to estimate this according to hidden Markov model, right? And now the Y's are hidden, right? They're latent variables. So this, and by the law of total probability, or marginal law of total probability, this guy can be written as, this probability can be written as the sum over all possible Y's. So maximizing, finding the parameters of the model that maximizes this is equal to find the parameters of the model that maximizes this. Why might we want to do this? Well, supervised data is often hard to acquire, right? Like, we actually have to ask someone to manually annotate the part of speech tags of these sentences. That's very expensive, right? Unsupervised data is plentiful, just download some text, right? So, we might just want to, maybe if we just train this in this unsupervised way, we can learn the Y's that correspond to part of speech tags. And there's things in between, right? We could have a small set of supervised data and then a large set of unsupervised data. And we want to be able to train on everything that we can, right? That's called the semi-supervised setting. But in order for that to work, we need a way to do the unsupervised way setting as well as a special case. And you could use these probabilistic models to do other things, right? You could do, for example, outlier detection. Here's a sentence that seems really, really, really unlikely according to our hidden Markov model. Can we, do something with that? Like, flag it for some downstream application. And as part of Mini Project 2, you can do that to, you could generate new sentences. Right? If you train a hidden Markov model on some corpus of data. So the standard algorithm for training hidden Markov models is called the EM algorithm, also known as Baum-Welch. Right? So if we had the Y's, then we could just solve using the closed form formulas, which are maximum likelihood. Right? The maximum likelihood closed form formulas. If we had the parameters of the model, we can predict the Y's. Right? So this is sort of a chicken and egg problem. We have neither. Right? So we do something kind of obvious. We initialize our parameters of the model arbitrarily, let's say randomly. Then we predict the probability of Y's for each training X. It's called the E step. And then given these Y's, we estimate a new parameters of the model called the M step. Repeat until we converge, or until we get bored. So this step is trivial because it's the supervised learning. It's basically the supervised learning setting with the closed form formula. This step is the step that's hard. Right. So given some current parameterization of the model, could be random, could be arbitrary in the very first step. For every training example, which is just a sentence, we want to predict this probability distribution. Right. We want to predict the token at each part of speech tag at each token in the input sentence. This encodes the model's beliefs about the distribution, right? And you can think of this guy as the marginal distribution of each token in Gaussian. So this is the matrix formulation, and I recommend when you implement this in homework to use the matrix version. It's orders of magnitude faster than writing for loops in terms of running time. And this is the maximization step. Basically the exact same thing, except counts. Instead of hard counts, we have soft probabilistic counts. But otherwise, it's the exact same formula. So now let's talk about computing these quantities. These are the quantities we want to compute. Let's talk about how do we compute this. And it's done using the forward backward algorithm, which is also a version of dynamic programming. It's structurally extremely similar to the Viterbi algorithm. So I'll go through it pretty quickly. So alpha sub z is basically this is the probability of observing the first the first I words and the I part of speech type being z, right? Given the parameters of a model. Beta is the reverse probability. It's the probability of observing the remaining words, given that the part of speech tag at token I is z. And it turns out that if you can predict and compute this marginal, what is the probability that the ith token is z, right, by just doing this? And this is just simple. This is basically just simple arithmetic after you combine these two terms. So then the challenge is, can we compute these alphas and betas efficiently? Right? So if you want to compute the transition from A to B for overall possible tokens in the sequence, let's get this. So the forward algorithm looks a lot like the Viterbi algorithm. We want to solve this alpha. So I indexes the location in the sequence, and z is the part of speech tag. We want to compute this for every location in the sequence and every part of speech tag. Right, the naive approach, again, you go through all possible. If you go through all possible sequences of length I-1, it takes exponential time. But we can compute it recursively just like Viterbi. And in fact, it exploits the exact same property of Viterbi. The main difference between Viterbi is that Viterbi does a maximization step here, and the forward algorithm does a summation step. That is the main difference. Because the Viterbi algorithm is interested in the most likely sequence, and the forward algorithm is interested in computing the total probability of observing any sequence that ends with the ith token being z. Backwards algorithm is simply just a backwards version of this. And this is the whole forward backward. Again, I'll have a more detailed description in course notes to supplement this lecture. And we will load your recitation on this next Tuesday as well. So you run forward, you run backwards. For every training example X, you compute the marginal probability of the ith token being z. And then that is the entire algorithm. I know I went over that pretty quickly, but it basically is structurally almost identical to the Viterbi algorithm, and you could look at it in detail later. Yes?
How do you know that the result of this is contemporary to something which is robust, independent of the starting A?
How do we know that the conversion of this is robust, independent of the initial conditions of the algorithm? We don't, and in fact we know that it is actually quite bad. So what people often do is they restart this process multiple times with multiple random initializations, and they pick the most reasonable model. Cross validation. You asked the question that in the next slide. Just to recap, today we looked at sequence prediction using hidden Markov model, which is a sequential version of naive Bayes. It models pairwise dependency, so adjacent pairs of predictions at a time directly in the model. It's compact because it only models pairwise dependencies, right? So it doesn't have this exponential growth in the number of parameters. The main limitation is, of course, it's still making a lot of independence assumptions, right? Just because you're modeling pairwise dependencies doesn't mean you're modeling everything there is in language, right? There are many times when you're speaking and you're generating sentences, and the way you're thinking about generating sentences are much richer than just pairwise dependencies. Right? That's the main limitation. Of course, any model has limitations, and you have to make these limitations in order for the model to be tractable. Right? Any questions? Yes?
Yeah, I'm a little bit confused. What is the output of unsupervised algorithm? So
You estimate the parameters of the model. You estimate all the parameters of the model. You estimate all the parameters of the model using only the x's, while observing only the x's and no y's. So in supervised learning, if you observe the y's, the estimation of the parameters of the models is a closed-form formula, just like in naive Bayes. In unsupervised learning, we don't have that. We don't have observing this. But we can, if we had a guess of the probabilities, then we could estimate the parameters of the model, just like in the supervised learning case. So what we do is we do alternating. We start with an initial guess of the parameters. Then we estimate this quantities, and then we re-estimate the parameters. Yeah.
So then, if we also want to predict y's in unsupervised case, we will still need some mapping between like the final parameters that the unsupervised model learns and well, basically what I'm saying is that these parameters will basically that unsupervised model learns
May not be interpretable.
Yeah, may not be interpretable.
That's correct.
Yeah.
Okay. So what people often do in practice is semi-supervised, where you have a small supervised set that you do this as your initialization, and then you do this on the whole data set. Okay, so next week, Tuesday, we'll have a we'll be talking about deep generative models, which, and okay, so Tuesday we'll be talking about deep generative models, which is basically just a recent applications lecture, so nothing on it will be relevant to the homework or the final exam. It's just an application of these types of probabilistic models combined with deep learning. And then we'll talk more about unsupervised learning, and the remaining lectures will be largely focused on unsupervised learning. And just a reminder, the recitation is next Tuesday at 7 p.m., which is a recap of the 30 and 4 backwards.